Dear students, today I am giving the sixth video on function analysis. In last classes we already studied in detail the projection theorem and Rees representation theorem with the proof. There we have mentioned that is both the theorems defined on a complete space. But the completeness is essential in both these theorems. That can be shown by or that can be explained by means of an example. So show by an example that completeness is essential in both projection theorem and Rees representation theorem. That's what we can explain by using this example, that is x equal to c naught naught with inner product xy equal to sigma j equal to 1 to infinity xj yj bar, or x is what x1 x2 etc. y equal to y1 y2 etc. is a notation. You just see the notation. We know that C naught naught is not complete. That we have studied. Now define fx equal to sigma n equal to 1 to infinity xn by n, where x is what? x1, x2 etc. Clearly f is linear. What is the modulus of fx? It is modulus of sigma n equal to 1 to infinity xn by n, which is less than or equal to sigma n equal to 1 to infinity modulus of xn by n. Okay. And we can make use of Holder's inequality here. That is, by using Holder's inequality, it is less than or equal to sigma n equal to 1 to infinity 1 by n square raised to 1 by 2 into sigma n equal to 1 to infinity mod xn square raised to 1 by 2. Holder's inequality ഓർമ്മയുണ്ടല്ലോ എന്താ for 1 less than p less than infinity and 1 by p plus 1 by q equal to 1, sigma j equal to 1 to n mod aj bj less than or equal to sigma j equal to 1 to n mod aj raised to p raised to 1 by p into sigma j equal to 1 to n mod bj raised to q whole raised to 1 by q. You take p equal to q equal to 2. So sigma j equal to 1 to n mod aj bj is less than or equal to sigma j equal to 1 to n mod aj square raised to 1 by 2 into sigma j equal to 1 to n mod bj square raised to 1 by 2. The same way you are taking here 1 by 2, p equal to 2, q equal to 2, or 1 by 2 plus 1 by 2 equal to 1, and substituting here or using or replacing here, we get the result as per the Holder's inequality. And what about the first part? That is sigma n equal to 1 to infinity 1 by n square raised to 1 by 2. Sigma n equal to 1 to infinity 1 by n square. That is an infinite series. And the sum of its value, that is what, pi square by 6 raised to half. And the other part is actually, that is nothing but norm x for all x in x. That is modulus of fx square is less than or equal to pi square by 6 into norm x square, which implies norm f is less than or equal to pi by root 6. That is, f is bounded or f is an element of x dash. Put f equal to capital F equal to z of f, the zero space. Here f is a non-zero bounded linear functional directly, or zf is a non-empty proper closed subspace of x. Here x is c naught naught. Is actually what we have done in the last theorem, the Rees representation theorem. In proof we have discussed this part. That z is an element of f perp. It is clear that f perp is subset or equal to x. What is x? C naught naught. This implies z is an element of c naught naught, or z equal to z1, z2 etc. zm, and all other terms 0, 0 etc. Define xn in c naught naught as xnj. What is xnj? That is 1 if j equal to n. Other one, minus of m plus 1 by n if j equal to m plus 1 equal to 0 otherwise. In that way we define. Then xn is an element of c naught naught because all other elements are zeros. Here xn is actually 0, 0 etc. 0, 1, then 0 etc. When it is m plus 1 you are getting minus m plus 1 by n, and all other cases 0. Now f of xn, that is equal to, what is that to substitute? 1 by n plus minus of m plus 1 by n divided by m plus 1. M plus 1 cancelled. So what do you get? 1 by n minus 1 by n is equal to 0. Or xn is an element of f for all n. Now consider inner product zxn. That is equal to zn for all n. but Z is an element of F perp, Xn is an element of F, so that inner product Z Xn is equal to 0 for all n in n, or Z of n equal to 0 for all n in n. So what is Z? Only all elements are 0, 0, 0, etc. 0, or Z equal to 0 in X. But Z is an element of F perp is arbitrary, or Z is an arbitrary element, and that F perp must be equal to Z0. So what you get? X is not the direct sum of F and F perp. Theorem, projection theorem നമുക്ക് അങ്ങനെ കിട്ടണ്ടേ. X must be the direct sum of F and F perp. Here it is failed. Our projection theorem is not satisfied when X is not complete. ഇതാണ് നമ്മുടെ argument. So we conclude that completeness is essential in projection theorem. എക്സാമ്പിൾ നന്നായി ശ്രദ്ധിക്കണം, നന്നായിട്ട് എഴുതിയിട്ട് തന്നെ പഠിക്കണം. പ്രൊജക്ഷൻ തിയറത്തിൽ കംപ്ലീറ്റ്നെസ് എസെൻഷ്യൽ ആണെന്നാണ് ഈ എക്സാമ്പിൾ കാണിക്കുന്നത്. ഇനി നമുക്ക് പറയാനുള്ളത് റീസ് റെപ്രസെൻറ്റേഷൻ തിയറത്തിലും ഇതുപോലെ കംപ്ലീറ്റ്നെസ് എസെൻഷ്യൽ ആണെന്ന് പറയണം. നെക്സ്റ്റ് ഷോ ദാറ്റ് റീസ് റെപ്രസെൻറ്റേഷൻ തിയറം ഫെയിൽസ് ഫോർ എക്സ് ഈക്വൽ ടു സി നോട്ട് നോട്ട്. എന്തുകൊണ്ടാണ്? സി നോട്ട് നോട്ട് ഈസ് നോട്ട് കംപ്ലീറ്റ്. അതായത് വി കനോട്ട് ഫൈൻഡ് എ റെപ്രസെൻറ്റർ ഫോർ എക്സ്. അതാണ് റീസ് റെപ്രസെൻറ്റേഷൻ തിയറത്തിൽ നമ്മൾ കാണുന്നത് റെപ്രസെൻറ്ററാണ്. ആ റെപ്രസെൻറ്റർ നമുക്കിവിടെ നിർവചിക്കാൻ അല്ലെങ്കിൽ ഡിഫൈൻ ചെയ്യാൻ സാധിക്കുന്നില്ല എന്നാണ് പറയുന്നത്. ശ്രദ്ധിക്കാലോ. വി ഹാവ് ഇ എൻ ഇസ് ഇൻ എക്സ് ഫോർ ഓൾ എൻ ഇൻ എൻ. വട്ട് ഇസ് ഇ എൻ? ദറ്റ് ഇസ് ദി യൂണിറ്റ് വെക്ടർ ഫോം. സി 0, 0, etc. 1, etc. zeros. What is in for all n in? That is 1 in at the nth place and all other elements are 0. Here f of n is 1 by n for all n in n. Now suppose there exists, if possible, അതാണ് നമ്മൾ ഉദ്ദേശിക്കുന്നത്, if possible there exists a representative y in x such that f of en equal to inner product en y for all n in n. So what is f of en? yn bar for all n in n. But actually what is f of en? 1 by n, or yn bar is 1 by n for all n in n, or yn is, you are getting as 1 by n. 1 by n it cannot be equal to 0 for all n in n. It implies y equal to, ഏത് ഫോമില വരിക? 1, 1 by 1, 1, 1 by 2, 1 by 3, അങ്ങനെ 1 by n etc. which is not an element of x equal to c naught naught, which is a contradiction for our argument. That is, if such a y exists, we are getting a contradiction. That is, there is no such y in x such that f of x equal to inner product xy for all x in x. This example shows that completeness is essential for the Rees representation theorem 2. That is our argument.